everybody. This is Suvarchala working as an associate professor in the Institute of Aeronautical Engineering, the Department of Computer Science and Engineering. In this video, I would like to explain about Stassen's matrix multiplication based on divide and conquer strategy. Normally, all of us are aware of how the matrix is going to be multiplied and what is the time complexity of matrix multiplication was already discussed. But anyway, we will see that how this matrix multiplication is going to be considered for the complexity or time complexity analysis. So basically, if you consider two matrices, for convenience sake, we will take initially as a square matrices of order n by n. So the definition of A multiplied by B, the product of A, B is an n by n matrix. Let us assume that it is a C in which each element is going to be computed by considering the row I of A and the column J of B. This multiplication, it will be multiplied together the first entries of the first row and first entries of the column in the respective column and the second entries of the second row and respective column and etc. Then add up all these products, we will get one element actually. Respective element we will get. So the number of scalar operations multiplies and adds in a straightforward algorithm we will be considering as a order of n cube. How it could be order of n cube? Is there any faster technique? Because we already we have seen in our asymptotic notations, if the complexity is in quadratic form or a cubic form or exponentiation form, for larger values of n, the complexity is going to be very fastly increasing the complexity. So that's why to reduce that particular order, that means the complexity is quadratic or cubic is there, if it is can be reduced up to quadratic etc., is our task to make our applications more efficient. So as a part of that, this matrix multiplication, let us assume that A, B, two matrices we are multiplying, each of them are having n rows and n columns. We will get a C matrix of n rows and n columns. As an algorithm, I is representing rows of the and J is representing columns and K is representing column of the respective C. If you observe this algorithm, nesting of the three for loops are there. So in addition to these additions, we will have the complexity of order of n cube, because nesting of three for loops are there. But just by using our normal tabular column method also, the complexity of this matrix multiplication is order of n cube. So n by n, B is multiplied by n by n, C n by n is going to be considered as K is equal to 1 to n, AIK multiplied by BKJ. So that's why we will get the time, three nesting of for loops are there. So that's why that time complexity is equal, T of n is equal to order of n cube, which is considered to be as a high time complexity actually. So that means, is any possibility of reducing this complexity? Cube complexity can be reduced at least square, or it can be reduced in between square and cube. That is going to be our task, so that matrix multiplication time can be reduced. Because when we are going to execute or when we are going to multiply two matrices of less orders, if n value is less, there may not be much difference. But if n is going on increasing, for some practical applications, if n value is 50, 100, etc., 100 by 100 matrix, 200 by 200 matrix, etc., if you would like to use specifically in some certain scientific applications, etc., there it is the time taken to do such type of multiplications will be very, very high. So that's why we can consider that matrix multiplication time complexity reduction is one of the crucial tasks to us. Now, we have been discussing in previous videos about divide and conquer techniques. This divide and conquer technique can be used, whether we can use for this matrix multiplication or not, we will see first. So that means we have to check whether divide and conquer can be applied for this matrix multiplication. First question. Second one, whether it is applicable, is any reduction in the time complexity occurs or not. That we will see in the immediate slides. So, A is a matrix, B is a matrix. If you are going to multiply, for example, we will take a least order, that is 2 by 2 matrix. So, 1 by 1 means it's individual scalar element only. So, that's why next n value will be 2 by 2 matrix if it is square matrix we are considering now. So, this is the lowest value of n for which this 2 by 2 matrix, for which without having any for loops directly you can do actually. So, how we are doing here? First row, first column. So, that's why A0 multiplied by B0, A1 multiplied by B2. First row, first column. That is the 1, 1 element. First row, second column gives the 1, 2 element. Second row, first column gives the 2, 1 element. And second row, second column, 2, 2 element. So totally how many multiplications and how many additions are there? Normal multiplications, normal additions. We have in each of these 2, 2 multiplications, that is 8 multiplications are there. And we have 4 additions are there actually. So if you are going to divide our each matrix into 2 by 2 matrices, then the respective multiplication of the 2 by 2 matrices, 2 by 2 matrices consists of 8 multiplications and 4 addition operations actually. Now we will see, is it faster way if you able to divide our entire matrix into base matrices of size 2 by 2 size. So that means we are going to divide a matrix into, that means when we have a 2 by 2 matrices, if you would like to divide, it may consist of scalar additions and scalar multiplications. So that's why how the division is going to be carried out. This can be carried out, a division can be carried out if you are able to represent n value is some power of 2 power k. That means if matrix is 4 by 4, S. What is n value? N value is 4. N value 4 means which can be represented as a 2 square. So 4 by 4 matrix you can represent. 4 by 4 matrix means it will consist of 4 sub matrices of 2 by 2 matrices. For example, you may be having A11, A12, A13, A14. Similarly, A21, A22, A23, A24. Similarly, A31, A32, A33, A34. And A41, A42, A43, A45. A 4 by 4 matrix. So A4 means n value is 4. It can be represented as a 2 square. So that's why we can divide our matrix into 4 submatrices. Each submatrix of order 2 by 2. In each, the submatrix can be considered further as a, let us assume that we will represent with an element A11. This is A12. This is A21. This is A22. So like that we can represent. Then what happens? This A11, A12, A21, A22. Again, these are all, if you consider as a single elements, then it is again in the order of 2 by 2 matrices. We can use same thing. So similarly, it was represented, each matrix is represented as a C11, C12, C21, C22 and A11, A12, etc. When you are using these capitals, uppercase letters as a, each of them is a 2 by 2 matrices. If you are considering it as a single element, then our C11, C12 are going to be in the form of like this. That means we are going to have our C11 is equal to A11 dot multiplied by B11, A12, B21, and so on and so forth. Normal 2 by 2 matrix multiplication can be considered for us. Now, we are going to calculate the values of C11, C12, C21, and etc. So, when we are transforming our entire matrix, that means dividing. We are dividing our matrix into sub-matrices of the minimum size, that is 2 by 2 matrices of n size is 2. Then this is going to be easily computable by us. That means transform the problem of multiplying AB, each of size n by n, into 8 sub-problems. Now you observe 8 sub-problems are there. So 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplications. Because here 8 multiplications means each of A, B are considered as having some matrices of order n by. So that's why 8 multiplications are there. We are transforming the larger problem into 8 smaller problems of multiplications of matrices of size, smaller sizes. Each of size is n by 2 by n by 2, if you observe. That's why I told you if it is 4, n by 2 by n by 2 means 2 by 2 matrices. If it is 8, 8 can be represented how? 2 cube. If n value is 8 means 8 by 8 matrices is there. 2 cube it can be represented. If it is 2 cube, what happens here? We are going to divide our entire matrices into various forms of 2 cube means you are going to get as a 8 problems. Problems can be considered. So like that we are going to divide into smaller sizes of matrices and we will try to multiply so that combining of the results are going to be considered by using this divide and conquer technique actually. So according to the divide and conquer, 8 multiplications are there. So 8 into multiplication means again it is a matrix multiplication, T of n by 2 plus a n square. This a gives number of additions here. So number of additions, because addition of 2 matrices you observe, this is one matrix, this is one matrix if you are going to consider. So A11, B11, one matrix, after multiplying we will get a matrix of order some n by 2, n by 2. B1, B12, B21, again after multiplying we will get a matrix. So a matrix is added to another matrix means again matrix addition complexity will be there. In a matrix addition complexity, what is the time complexity of matrix addition? 2 nesting of loops will be there, for loops. For I, row, O, outer loop, for J as a column inner loop, so that internally within the inner loop we will add respective elements of A and B stored in some other matrix. So what happens? The time complexity of matrix addition is n square. So many additions are there, 4 additions are there. We are going to get 4 into order of n square. So that means it is order of n square only. So this 8 T n by 2 means division of each matrix into sub-problems, 8 sub-problems. And this a n square is a time taken for addition of the matrices. A matrices, A is a constant. So in this example 4 we are considering. So in the previous, depending upon the size of the matrix, no more number of additions can be considered. So what is the recurrence relation of this? Divide and conquer is a recursive method. No, because of this recursive method, the recurrence relation for this matrix multiplication process by using normal divide and conquer strategy is T of n is equal to 8 T of n by 2 a n square, which is equal to order of here also. We are going to, by using our matrix addition as well as the T of n by 2 is, again we will do multiplications, no, it will come under the n cube only here. So that's why it is order of n cube, which is the n square is for addition. That means by using our theorem, Master's theorem, or by using recurrence relation, solving a recurrence relation by using substitution method, this results as order of n cube. So that's why even we are applying our strategy, divide and conquer strategy, we are unable to reduce our time complexity of normal matrix multiplication actually. So we'll consider one more example you observe. So always if you unable to represent your n in the form of some 2 power k, then what happens? Then add some rows and columns to each of these matrices to make your n as 2 power n, 2 power k. So for example, what is this here? 3 by 3 matrix and 3 by 3 matrix. 2 3 by 3 matrices. Can we represent 3 as a 2 power k? No. So what is the next value to represent our n value, which can be represented as some 2 power k is 4. 4 can be represented next immediate value. That is the next immediate value which can able to represent as a 2 power k is 4, which can be represented as a 2 square. That means instead of 3 by 3 matrix, I should have 4 by 4 matrix. Then only the division can be done properly as a square matrix division of size 2 by 2 or whatever. So that's why if you want to use, if the given matrix is 3, but we would able to use this divide and conquer strategy for 2 power k equal to n only, then you add some rows and columns to our existing matrices as elements are 0 elements, so that our matrix becomes of required size. That means 3 by 3 means now I have to make it as a 4 by 4 matrices. So 4 by 4 matrices means 1 row, 1 column has to be added. 1 row zeros and 1 column of zeros are added. Now this becomes as 4 by 4 matrices. While doing this process after multiplication, we won't get any additional results. So results are not going to be get disturbed. 1 row, 1 column added, no. So the last row, last column. After multiplying also, the last row and last column values will be zeros only. There is a rule is also there in matrices. By adding number of rows and number of columns as zeros to a matrix, the matrix value doesn't change. So that's why if you multiply, you just multiply this, you will get 3, 3, 3, 3, 3, 3, 3, 3, 3. A 3 by 3 matrix, each element is having 3. By adding zeros also, I'll get say a 3 by 3, 4 by 3, 4 by 4 matrix. All elements are 3s except the last row and the last column having zeros, which can be discarded by us. It doesn't make any change in our original matrix actually. So that's why adding additional columns and additional rows of 0 values may not or will not change the result of the product, in the result of the product of these two matrices actually. So that's why if it is not satisfying the criteria of n is equal to 2 power k, you make 2 power k value, the n must be changed to the next immediate value for which it is equivalent to the 2 power k. For example, I have 6 by 6 matrix. 6 cannot be represented as some 2 power k. So what is 2 power k? 2 power 1 is 2, 2 square is 4, 2 cube is 8. So after 6, next value is 8 I can take n, which can be represented as a 2 cube. 8 means 2 rows and 2 columns must be added to my original matrix as zeros, so that it can be considered as a 6 by 6 as a 8 by 8 process is going to be continued. So when we are doing this here, you observe here our C11 is equal to 4 ones and we have to divide, no? So now we are dividing like this, and one is this is A11. Previously I have shown A12, A21, A22, B11, B12, B21, B22. This is C11. We will get C12, C21, C22. So these are the individual matrices multiplication and addition of the respective matrices we will get. Then you add these into a new matrix as A11 as the first element and C11, C12, C21, C22. We'll get the original product as 3330, etc. So an algorithm for this divide and conquer by using recursive. So what we are doing previously, you observe how many number of times we are doing? 8 times multiplications we are doing. 8 times we are applying multiplication means 8 times we have to call the same algorithm again. So square matrix only we are considering here. Please observe that square matrix multiply by using recursive, using divide and conquer. This is an algorithm. Two matrices we are passing, n rows and n columns. C is equal to a matrix of the product of these two matrices of n by n. Now if n is equal to 1, directly you can do it actually. C11 is equal to A11 star B11 or A11 multiplied by B11. Simple scalar multiplication. When we are going to, otherwise we have to divide our matrices into submatrices. As we explained in the previous expression here. Like this we have to divide our matrices into submatrices. By using this, our C11 is, so how the C1 is computed? You observe here, C1 is computed product of two matrices and a product of another two matrices. Two times I have to call my Stassen's matrix, a divide and conquer strategy. So if it is not equal to 1, recursive algorithms are that only, no? So we are calling square matrix recursive A11, B11, A12, B21. Like that we are calling, where A11, B11, etc. are submatrices again. So if again it is going to be reduced, if it is 1, it is directly multiplied, otherwise recursive process is continued. If you observe this recursive process analysis, that recursive version of divide and conquer is also A, B and C into 4 submatrices each. We can compute resulting matrix of C by multiplying two matrices of size n by n. We will make 8 recursive calls of the again multiplication again. And order of n square is for theta of n square is depending upon the lower bound, upper bound consideration. So theta of n square is going to be for addition of matrices. But even then what happens, we will get here the complexity is T of n is equal to theta of n or B of n if n is equal to 1. Otherwise this is recursive. 8t of n by 2, half of we are dividing, plus theta of n square. As we earlier discussed, theta of n square is for addition of matrices actually. So where T of n is running time of the n by n matrix, and by using Master's theorem, this results as our recursive calls order of n cube. That means even though we are applying our divide and conquer strategy, the time complexity of our matrix multiplication remains same. That is order of n cube or theta of n cube only. That is, we are going to now discuss how these recursive calls can be reduced or not. So strategy can be applicable, but even though we are applying divide and conquer strategy, 8 times it is doing, because of that it is reaching again 8t by n by 2, means by applying a value as a 8 and b value as a 2, direct Master's theorem, we will get an order of n cube only. So that's why what is our task now? It is not reduced. Original matrix multiplication by applying divide and conquer also, same time complexity we got actually. Same order of growth time complexity we got. So that's why our task is now, can we do a fewer recursive calls which can make us our matrix multiplication complexity can be reduced further? Is it possible or not? That is, fewer multiplications of n by 2 submatrices can be considerable or not. That is, number of multiplications can be able to reducible or not. Instead of 8, it can be 7, 6 or like that. If you are able to do, up to certain extent, the time complexity can be reduced. So this, based upon this need, in 1969, Stassen, a great mathematician, found a different approach by using which we can reduce the matrix multiplication complexity a little bit. Seems to be little bit in our order of complexity, but when n size is going for higher and higher values, huge values of n, lot of time can be saved by us by using this Stassen's matrix multiplication. So the mathematicians were surprised by seeing this type of multiplication process. Stassen's algorithm makes use of the same divide and conquer technique, which just now we discussed. We have to consider n value as able to represent as a 2 power k and so on and so forth. So same we are Stassen also considered divide our matrix into submatrices of up to size of 2 by 2 etc. But instead of using 8 multiplication, that is 8 times recursive calls, Stassen uses only 7 recursive calls. So Stassen uses only 7 recursive calls rather than 8. That is, one recursive call was reduced by Stassen's multiplication technique. So this is enough to reduce our runtime complexity to sub-cubic time. So instead of having cubic time, if you are able to reduce even one recursive call also, a lot of difference will be there. But remember, for larger values of n only. For smaller values of n, we may not find much difference actually. The key to Stassen's method is to make the recursion tree slightly less bushy. Stassen's method is not all just like obviously we can do it actually. Stassen's proposed certain number of equations. By using these equations, instead of having our A11, because multiplication of a 2 by 2 matrices, we have 8 multiplication, 4 additions, 2 by 2 matrix. How many we are getting? A11 we are going to get, and A11, B11 plus A21, B12. This is one element. Similarly, 4 elements are there. So in each element, how many multiplications? 2 multiplications, 1 addition is there. Similarly, based upon this concept, Stassen's multiplication, Stassen's proposed to some equations. So totally even 12 equations were proposed by Stassen's for multiplying a matrix of order 2 by 2. Base only. Base size only we are considering. So what are these entire equations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 equations are there. In this 11, various computations have been made actually to compute our C11, C12, C21, C22. That is to compute our elements of the product matrices of order 2 by 2. These 11 equations are used. What are the operations these 11 equations consist of? These 11 equations consist of some additions, some multiplications again. Of course, subtraction is also one kind of addition only, addition of negative number. So that's why it consists of some additions and some multiplications. This CIJ is computed by using 7 multiplications and 18 additions. Please observe, additions are increased. But even then, these additions are increased, the time complexity is not going to be increased because each addition takes order of n square only. So even 18 or 20, whatever it may be, 4 or 5, it will be having n square complexity only. But multiplications, if you observe that number of multiplications previously it is 7, now it is reduced to here. Previously it is 8, now it is reduced to 7. That means one multiplication reduced. It means that one recursive call was reduced. So these equations have to be directly used to compute the product of two matrices of order 2 by 2. So the procedure is, we are going to write Stassen's matrix multiplication. If n is equal to 2, we are doing these equations you have to express, and that means you are going to compute directly by using normal multiplication, or otherwise we are calling. So instead of using here, this is a recursive procedure multiplication. Instead of using these expressions, replace these expressions with our Stassens. So we replaced these with our Stassens. What are the Stassens here? P plus S minus T, etc. we are computing actually. So by using Stassens, we can replace, and number of recalls we are calling here a 1, 2, 3, 4, 5, 6, 7. 7 calls are there if you observe these values. And we computing C1, C2, etc. That means if it is normal 2 by 2 matrix, we are computing normal way because it's a simple thing. If it is more than 2 by 2 matrices, we are recalling our, recursively we are calling our algorithm, Stassen's algorithm, by using these for 8 equations. That is, these are the P, Q, R, S, T, U, V for them. These are all called because it consists of multiplications. Wherever multiplications are there, we are again calling Stassen's matrix with reference to respective dimensions actually. So we are calling totally 3, 4, 5, 6, 7 times recursive calls are there. By using those values, we are computing the values of C11, C12, C21, C22. So this process is continued for the order of 2 by 2 up to the order of 2 by 2. If it is more than 2 by 2 order, it will go this part actually. So how this Stassens is reducing? This Stassens is reducing our time complexity of our matrix multiplication by reducing one recursive call. You may be thinking that this one recursive call may not give much differences. Of course, for n values, lesser values, it won't give much difference. And for larger values only, it gives a lot of difference actually. So to solve this recurrence relation of Stassen's algorithm, so our Stassen's algorithm recurrence relation 7 times we are calling now. So that's why our A value is 7. T every time we are dividing by 2. So n by 2 plus a n square. A is the number of additions. This is for n is greater than 2. If n is equal to less than or equal to 2, you can compute directly the value. So we'll solve this actually. So while solving, just keeping on going, substitution method you can use or Master's theorem. So if you are going to use substitution method, so T of n by 2, we will substitute in T of n by 2 place, n in n place as the n by 2, then we will get it as a 7 square. T of n by 2 square plus 7 by 4 a n square plus a n square. That means in case of n, we are substituting n by 2. Again here also we are going to substitute n by 2. It's keeping on continuing, recurring, no? So that's why. If we are keep storing n by 2 again, it will become as a n by n 2 cube, 7 by 4 n whole square and a n square plus 7 by 4 into a n square and a n square, etc. So if we are continuing like that, we will get kth term as a, you observe here, this is 0, 1, 2. So kth term means 7 power k minus 1 will be there. T of n by 2 power k minus 1 plus a n square into 7 by 4 whole power k minus 2 plus 1 we are going to get. So in this case, if you are able to represent n is equal to 2 power k, yes, we can represent. That is the initial criteria we consider. So if you are able to represent n is equal to 2 power k, then we will get 7 power logarithmic operation. So we will get order of n log power 7. N log 7 will be there to the base 2 by 2, no? So to the base 2 will be there. So the time complexity is going to be 2 power 81. N power 2.81. So that means here n is equal to 2 power k means we will get k is equal to log n to the base 2. So we will get log n to the base 2 is equal to k. So by substituting this k value in this, we will get our process as 7 power is there, no? So we will get 7 power log n to the base 2. That is By substituting that, we'll get k value n power log 7 to the base 2 will be there. And totally we will get complexity as n power 2.81. Log 7 means we will get 2.81. So 2.81 means previously we got n cube, no? So a little bit reduction is there in time complexity. So by using Master's theorem also, for a is equal to 7, b is equal to 2, and by using f of n is equal to theta of n square, we will get function f of n is equal to order of n log b, n log a to the base e minus epsilon. So which is equal to n log, what is our a value? A value is 7, b value is 2. By substituting that, we will get n log 7 to the base 2 minus epsilon, which is approximately equal to n log 7 to the base 2 is 2.81. Right? So, such a way you can reduce the time complexity by using Stassen's matrix multiplication technique. Again, through divide and conquer strategy only. So, it reduced, but not drastically. Very small amount of time was reduced. Then, why we are not using this Stassen's multiplication in normal applications? Because whenever we would like to multiply, irrespective of this time complexity, normally we will use our normal multiplication technique only. So, by seeing itself for normal values or smaller values of n, taking or doing this entire process of dividing and conquering, etc., is not necessary, because the time taken to normal multiplication and even Stassen's also, the difference may not be that much if smaller values of n. So that's why it is not that much popular, because the reduction of time is not considerable thing in most of the for smaller values of n. Another one is it's not always practical. And constant factor is larger than the naive method. Constant factor means when we are using this addition of matrices, etc., we are going to take, no, it is more than, for smaller values it's okay, but more larger values or certain values, up to certain values, your addition of matrices, more number of additions means it may increase our time complexity also. So specially designed methods are better on sparse matrices. For example, if the matrices are sparse, such type of calculation of multiplication time complexity by using Stassen's with some complex procedures. Instead of that, other methods of multiplying sparse matrices is better. So that's why the sparse matrices, whenever the matrices are sparse, methods are tailored for sparse matrices are faster than these even Stassen's matrix. Most of our scientific applications, sometimes we may be having sparse matrices also. And one more problem is the issues of numerical instability. Numerical instability means if it is other than integers, if you are going to take the error factor, because float values, if you are going to take in such cases, the truncations may occur in such cases, the error factors are going to be more actually, comparing with our normal multiplications. These are all some of the problems are faced while using our Stassen's multiplication in our frequently using the Stassen's multiplications in our normal applications of matrix multiplications. So, based upon this discussion, the Stassen's multiplication needs only 7 multiplications of n by 2 size matrices, not 8. So that one recursive was reduced. Because of that reduction of one recursion, the lots of time can be reduced also. And moreover, one more problem is recursive uses a lots of space. Of course, this is a problem whenever we are going to apply our divide and conquer technique, actually being a recursion process actually. And it requires theta of n square arithmetical operations for addition, and that may take a lot more time because more additions are required also. So that's why It's a not a just a theoretical result. It is not just observed or evaluated based upon our recurrence relation, solution, process, etc. But even we can test for practically also. It gives a lot of difference in time taken to execute our matrix multiplication. But I have been stressing upon that if the value of n is more than larger values, specifically useful for n is greater than 50, this is going to be considered as a little bit better results comparing with our normal multiplications. 50 by 50, 100 by 100 as etc. The order is going to be very, very keeping on increasing in such cases. This is going to be very much useful. For normal smaller applications which we are doing, our normal simple applications, we can go for our normal matrix multiplication technique also. Afterwards, after Stassen's multiplication technique, better result also researchers provided us better results in which our time complexity will reduce to 2 power n power 2 power order of n power 2.375. You observe it drastically how much it is reduced to. In case of Stassen's, n power 2.807 is there. Now n power 2.375. So almost 0.5 was reduced power. That means the Stassen's algorithm was asymptotically faster than the basic procedure of multiplying matrices. We are using asymptotically. That means as n is growing, our Stassen's algorithm is more faster comparing our normal matrix multiplication. Better asymptotic upper bounds for matrix multiplication have been found because Stassen's matrix multiplication was given in 1969. From there onwards, researchers have been working to reduce the time complexity of matrix multiplications. Some better results are also out actually. That is most asymptotically efficient algorithm for multiplying an n by n matrices currently is designed by Coppersmith and Vinograd's algorithm, which has running time as n power 2.376. So now the fastest known method is having n power 2.376 and with the best well-known lower bound is omega n square actually. So that's why if more faster way the multiplication has to be done by us, that too asymptotically values of n, then we can go for the next method also actually. It all depends upon our application requirement actually. So by using this Stassen's multiplication, this divide and conquer can be considered as one of the applications of Stassen's multiplication. Of course, without Stassen's also divide and conquer can be applied to matrix multiplication, which doesn't make any difference of time complexity. So that's why just applying divide and conquer on normal multiplication is no use at all. So that's why if you would like to apply Stassen's matrix multiplication, then only divide and conquer strategy can be used by us so that a little bit time complexity can be reduced. As we have seen till now, so normal divide and conquer application of divide and conquer strategy on matrix multiplication doesn't result any better way. So that's why if you would like to use Stassen's matrix multiplication only, better use this divide and conquer technique. That's why we discuss this Stassen's multiplication as one of the applications of divide and conquer technique. So various applications are there. So we have been discussing various applications in few previous videos about divide and conquer applications, starting from binary search, quick sort, merge sort, and now today in this session as Stassen's multiplication. In addition to this, most of various applications are there. Depending upon the respective domain requirement, we can apply this technique actually. So computational geometry, we can find the closest pair of the points, divide and conquer, find the convex hull. For that also we can apply divide and conquer strategy. Mathematical calculations, Converting a binary to decimal, we can use divide and conquer. Integer multiplication, because we started this divide and conquer strategy with our integer multiplication concept only. So matrix multiplication, just now we have seen as one of the Stassen's matrix multiplication. Matrix inversion, this is the most challenging job of mathematical applications, because inverse is required for us. Set of simultaneous equations, if you would like to solve, we need matrix inverse is required. So if the order is keeping on increasing, calculation of inverse takes a lot of time. And fast Fourier transformations and many more are there. These are all some applications to name, that's all. But various real-time applications, we will use this divide and conquer strategy. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.